Hello everyone, in this video I want to talk a bit more about the law of sines, and in particular what we call the ambiguous case involving the law of sines. And so when we're solving a triangle where two side lengths and the angle opposite of one of those side lengths is known, then there may exist 0, 1, or 2 triangles that can be constructed with that information. So in the pictures I have drawn over here, we're supposing that we know the two side lengths of little a and little b, as well as the angle of big A. And that's what I've tried to draw in these pictures so far. So here is our angle A, here is our side length little b, and I haven't drawn in our side length little a yet, because that side length little a being drawn into this picture and how we draw it in kind of helps us understand why this ambiguous case can show up. And so to help further explain the setup for these pictures, on the bottom of each of these triangles, I'm using a dashed line, because if we think about the setup for our triangle, if this is side length B, somewhere over here would be angle B, and then that last piece of information would be angle C and side length C. We don't know side length C, it's not one of our known quantities. This dotted or hashed line is supposed to represent side length C in our three triangles, and because it is unknown, we can kind of think of it as varying, being as long as is needed to construct the triangle if it is possible to do so. So when we talk about constructing these triangles with the given information, it's all going to come down to that piece of information we haven't drawn in yet, that side length A, and whether it is too short, the right size, or too long to draw some triangles. And so the first case we're going to consider where side length A is very, very short. And so remember, this is our angle C up here. We are not told what angle C is, so it can vary, which means we can think of our side length A as being able to pivot or be on a hinge. As we rotate angle A around our point up here, that's basically increasing or decreasing that angle C that would correspond to that point. But the idea is, no matter how much we rotate this short side length, if it's not long enough, it'll never actually intersect that bottom side length down here. So in this first case, that's where we have no triangles possible. And so in this first case, little side length A is too short to kind of connect down to our remaining side length to actually create a triangle. So the kind of follow-up question is, well, how short is too short? What's like the minimum length little a would have to be in order to make one triangle? And the idea is the shortest our side length A could be would be the length of this straight line coming down from our point up here, connecting to our side length C down here. So it's actually the shortest triangle we can make here is if side length A helps us make a right triangle. And well, if side length A helped us make a right triangle, then we can use right triangle trig to express the height h of that right triangle. And doing a little bit of right triangle trigonometry, we can see that this side length h that would be needed to make a small right triangle here would have to be equal to exactly b times sine of our angle A. So if our side length A is smaller than this quantity h, or b times sine of our angle A, writing h in terms of our known information, then no triangles are going to be possible. And so we can recognize these ambiguous cases by looking at little inequalities like this, although I prefer to just actually determine whether we have 0, 1, or 2 triangles by plugging this information into the law of sines and seeing what we get and interpreting that correctly. We'll talk a little bit more about that when we do some examples. So let's go ahead and move on to our second case, and that's when we have exactly one triangle. And we actually kind of mentioned that already in our first case. So if our side length A is just right so that it comes down straight down and creates a right triangle, then we can have one and only one triangle in this case. And that's going to be the case. So our one triangle case is when A is actually equal to that quantity h, when A is actually equal to b times sine of A. In that case, we have a right triangle. And so now the idea is, and this is what gets represented in this third case and third picture, is if our side length A in our second case was actually just a little bit longer, but not too long, well, if it was a little bit longer, then we could see that we could rotate it to the left and create an oblique triangle here, or we could rotate it to the right and create an oblique triangle out there. And so maybe our side length A is just about this long, still not longer than side length B, but less than side length B and longer than side length H, or bigger than b times sine of A. Then we could pivot that little bit of extra side length inward to create this oblique triangle, or we could pivot it outward to create this other oblique triangle, but with only acute angles. And so in our third case over here, we see that if A is a little bit longer than the length necessary to make this right triangle, but not too long, not longer than side length B, then we can actually create two triangles. So that inequality says A has to be between side length B and that number B times sine of A. And there's actually a fourth case that I forgot to draw in these original pictures here, but I kind of mentioned as we were going through these pictures. So let me go ahead and set that one up. So if A is longer than B, then that means we can't possibly pivot it inward to create a oblique triangle like we could in our third case. The only direction we have to pivot it would be outward. And so, sorry, I have to intersect that a little bit. But if side length A was really long, where A is bigger than our side length B, then we still could create a triangle, but we could only create one triangle. So these are the four special cases for the ambiguous case within the law of sines, kind of depending on that side length A with respect to this quantity B times sine of A and that other side length B. We're going to have either 0, 1, or 2 possible triangles that we can construct. So for certain application problems, we're going to have to use context clues to know which of the 2 triangles is the one we actually want. And for other more abstract problems, we're just going to have to find both the triangles, and that'll be our full answer describing and finding or solving both of the possible triangles. In this example, we were asked to solve the triangle ABC given the following information. We were told that angle C is 50 degrees, side length C is 40 units, and side length B is 50 units in length. And so we were told that angle C is 50 degrees. We were told that side length C is 40 units, and side length B is 50 units. And so we're not saying our triangle actually looks anything like this. This is just to help us kind of organize our information and recognize which kind of formula we might use to help us solve this triangle. And so if we look at the information given, we're given 2 side lengths and the angle opposite of one of those side lengths. That's a case where we can use the law of sines to help us solve this triangle. And that's actually the ambiguous case of the law of sines. And so we know angle C, side length B, but we don't know angle B. So I think that's the first thing we want to find is our angle B. And so we can use our version of the law of sines that says sine of angle B over side length B is equal to sine of angle C over side length C. So we don't know our angle B yet. I'm actually going to go ahead and call that B1, and I'll talk about why in a second. So that's going to be over 50. And that's going to be equal to sine of our angle C, sine of 50 degrees, divided by side length C, which is 40. All right, so we can solve this for sine of angle B1. Just by multiplying both sides by 50, we see sine of B1 is going to be equal to 50 times sine of 50 degrees, all over 40. So now if I enter that into my calculator, we should get just sine of B1, or 50 times sine of 50 degrees over 40 is equal to about 0.95756. And so this is the first place where we can check our ambiguous case to see if we have any possible triangles. And so for that, we have to remember the range of our sine function is from -1 to +1. And so if we ever get sine of our unknown angle is equal to a value outside of that range, like the right-hand side is a number bigger than 1 or less than -1, then we know that that's impossible. And that's the case where we have 0 possible triangles. So that is not what we have here. 0.9576 is less than 1. That is inside the range of our sine function. So that guarantees we have at least one triangle. And so we would find angle B1 just by taking sine inverse of that value, 0.957756. Although we may have a second possible triangle that we could find here. And in the picture, that second possible triangle, we'll consider the case where we have the oblique triangle, but with an obtuse angle. And so what we really have to now do is find what that second possible value for angle B could be in that triangle with the obtuse or large angle. To find that second angle, we have to go back to our unit circle and our trig functions. And remember, if we get one solution from a sine inverse equation, the other solution comes from pi minus our first solution. But that was our setup when we were working with radians. For a lot of these triangle problems, we're working in degrees. So instead of the second solution coming from pi minus our first solution, our second solution is going to come from 180 minus our first solution. Or in this case, 180 minus sine inverse of 0.95756. So that's an important thing to remember. All right, so now we can use a calculator to help us evaluate those expressions, and we get angle B1 would be 73.2 degrees, while angle B2 could also have a value of 106.8 degrees. So we're guaranteed at least one triangle exists, and that's going to be this first triangle with angle B1 with that acute angle. For the second triangle with angle B2 of 106.8 degrees, we might not be convinced yet that it actually exists. And so the way to check if it actually exists is to take that angle B2 and make sure that we can find that third angle. So our other known angle is 50, and so B2 plus C, or 106.8 plus 50, gives us like 156.8. That's enough room to find our angle that we'll call A2. And so how do we find that third angle? We'll just use 180 minus the two known angles. So that's 180 minus C minus B2 for angle A2 over here. And for angle A1, that'd be 180 minus C, or 50, minus angle B1. And so if we can't find that third angle, like we get A2 is equal to some negative number or something that doesn't make sense like that, that is our indicator that that second triangle doesn't actually exist. But because we're able to find that third angle that we're calling A2, and it's a value that makes sense, that means that second triangle actually does exist. We also found angle A1 to be 56.8. So now to finish this problem off, we have to find side length little a1 and little a2, that missing side length for our first possible triangle, as well as that missing side length for our second possible triangle. And so if we want to find side length little a1, we're going to have to use the law of sines with the version of little a1 in the numerator. Then we're going to need sine of capital A1 in the denominator, or sine of 56.8 degrees. And that's going to be equal to sine of C over side length C, or we could do sine of B1 over side length B1. But if we have the option of using exact information that was given to us, I say we should always do that. So let's set it up as side length C, or 40, over angle C, or sine of angle C, which is sine of 50 degrees. All right, so we can solve for little a1 by multiplying both sides by sine of 56.8 degrees. And then when you evaluate that, we get little a1 is about 43.7 units in length. All right, we also have to solve for little a2 for our second possible triangle here in the ambiguous case of our law of sines. So for that setup, we're going to have little a2 over sine of angle a2. So that's sine of 23.2 degrees. And that's going to be equal to side length C, or 40, over sine of angle C, or over sine of 50 degrees yet again. And little a2 is going to work out to be approximately 20.6, which makes sense because our sine function, as well as our law of sines, is basically saying as the angle gets bigger, our sine function gets bigger, and that makes our side length have to get proportionally bigger as well. And so that's what we see here. Angle A1 is bigger than angle A2, and so side length little a1 should be bigger than side length little a2 as well. So we have finished solving this problem. We found that there was two solutions, two triangles we had to solve for. So let's go ahead and organize our answer in a nice compact way. So remember, we're looking for angle A and side length A, as well as angle B here. So we found B1 to be equal to 73.2 degrees. We found A1 to be equal to 56.8 degrees. We found little a1, or side length a1, to be 43.7 units. That was for our first triangle. And for the second possible triangle, we got B2 was 106.8 degrees. A2, our other angle, was about 23.2 degrees. And that last side length, little a2, was about 20.6 units.